definition.
Thank you for having me. Let's host this out today. I want you to be excited for two reasons. One, it's almost time for lunch, and two, this is a fascinating topic that you're probably gonna enjoy. I definitely did, fall in love with it, and I want to thank Professor Thomas Keller. He had to leave. It's very unfortunate because he was the one who introduced me to this fascinating topic. So before I introduce you to topological quantum field theories, TQFTs for short, I have to give you a little bit of background. You have to know what a category is, what covariations are, and basically I'm going to be giving you definitions that are very loose in a sense. Like I'm not going to go through like all the rigorous details because we only have 15 minutes and we can be getting bogged down in those details. And also another thing, all my drawings, all my graphs are in 2 dimensions, but I'm going to be referring to n dimensions. So I'm going to be referring to the more general case. So what is a category? Okay, a category is a class of objects. You can think of it as a collection of objects. And then for any 2 objects in a category, you have a set of morphisms from one element to another element. Okay, you can think of morphisms as maps, but they are more general than maps. As you will see in a minute, what I mean by this. So if you think of it as maps, it has to satisfy the composition law, and it has to have an identity morphism. The reason why I'm drawing a cylinder there, that'll become clear in a few seconds. That's actually going to be a morphism in one of the categories that we're going to be dealing with. So examples of categories. We have the category of sets. The objects are sets. The morphisms are functions, taking one element to another element in a different set. We have the category of vector spaces, where the objects are vector spaces, and the morphisms are your linear maps, the usual linear maps that you represent with matrices and what have you. We have the Hilbert spaces, which is pretty much the same, but the objects are Hilbert spaces. That's norm linear spaces with where the norm is comes from an inner product. And then we have the category of covariations. In this case, this is where the morphisms are not going to be functions; they are going to be covariations. And the objects are going to be n-1 dimensional manifolds. All these manifolds are going to be oriented. You can take a more general case where they're not oriented, but I'm going to focus on the oriented case. So, what are covariations, right? That's the first question. You have to know what a covariation is. I thought the quality was going to be a little bit better than that. Okay, if you think of space, right, like we're here at this moment right now, you can think of space as an n-1 dimensional manifold, right? And then if you think of space-time, as we move through space-time, you can think of that as an n-dimensional manifold, one dimension more than the dimension of space, right? So that n-dimensional manifold is going to be your covariation. So in this case, we have, a cylinder is going to be a covariation. We start here on this S1 circle. You can think of that as the n-1 dimensional manifold that's representing space at this slice of time. And then you can think of this whole cylinder as a covariation taking you from point A to point B right here. So in this case, it's giving you a copy of the same n-1 manifold. That's because this cylinder turns out to be the identity morphism in the category of covariations. Just like you have an identity map for, in the vector spaces, you have, identity linear maps. So in this case, the identity morphism is going to be the cylinder. It's just taking this copy from this manifold to another copy of manifolds with a different orientation though. This has a different orientation. Why? Because if you take this, let's say it has orientation going this way, we'll draw the cylinder, okay, and then it has the reverse direction because this one is an in boundary. It's called an in boundary. You're going into the covariation this way, and you're going out the other way. If you take the same direction, if you flip it like this, then you're going to have something like this, right? Because these are topologically equivalent. You can flip it around, twist it. So this is different. These are 2 different things, and you're going to see why in a minute. It'll become clear soon. That's an intuitive notion about what a covariation is. Instead of giving you like the whole rigorous definition, giving you a more intuitive representation. So in that case, where you saw the cylinder, we were going from a connected manifold to another connected manifold. but it doesn't have to be that way. Like in this case, in the more general case, we can have disconnected spaces. So in that case, we have two n-1 manifolds, and we have the cobordism taking us from these two n-1 dimension manifolds to one n-1 manifold. So you can think of, let's say, this is you, and this is your partner, and you haven't met yet, and like in a few years you meet, and this is where the happy ending occurs. So you can think of it that way. So the cobordism is space-time, you know. So what is this whole business of taking disjoint unions? Why are we able to talk about disjoint unions and all that? Well, the reason is that a cobordism is a monoidal category. Now, what do I mean by that? A monoidal category has a well-defined operation, and maybe I'm not going to give you like the whole rigorous definition of what monoidal category is, but basically it has an operation, right? It has an operation that is well defined, and one thing I'm going to mention is that it has to preserve. It has to have a unit. So if we have, let's say, in the category of cobordisms, to be more general, let's say that we have this element, and let's call this element 1 to be the unit. That has to give us x, right? It has to have that unit. That's one of the properties that you're going to need in order to understand what's coming now. So an example of a monoidal category is a group, the category of groups, right? The operation is the direct product of groups. We have the vector spaces where the operation is a tensor product, so that's where that notation is coming from. I use the same notation for all of them, but basically that's the notation I use for tensor products in vector spaces. And we have the operation on the category of cobordisms is the disjoint union of manifolds. So, what do I mean by this? I'm going to show you a picture right here. If we use the disjoint union of cobordisms, you see we have disjoint union of these two cobordisms, and then we take this as the map, right? The morphism that is morphing these two n-1 dimensional manifolds to this disjoint union of these three n-1 dimensional manifolds, and then another disjoint union of cobordisms taking you to this disjoint union of two n-1 dimensional manifolds. So we're getting to the topological quantum field theories. There might be a few questions about these products and all that, but we'll get back to this in a second. I just want you to finally define what a topological quantum field theory is. So you have to know what a functor is. I'm not going to give you the whole rigorous definition again, but basically you can think of it as a map, taking objects in one category and mapping it to another category. So you can have like taking a functor going from like in the homology case, you can take a functor from the topological spaces, sending it to an abelian group or what have you. So in this case, we have a topological quantum field theory. It's a monoidal functor going from the category of cobordisms to the category of vector spaces. You can take it, you can define it in different ways. So you can send it to modules instead of vector spaces, or you can send it to Hilbert spaces. But just for the sake of just to give you an example, we're taking the vector spaces to be the target of the TQFT. Now, why is it a monoidal functor? Because it has to preserve the monoidal product. You will see in a minute what I mean by this. If we take, that C is our TQFT, topological quantum field theory, and we're taking objects from the category of cobordisms in dimension 2 to the category of vector spaces. So what is that TQFT doing? It's taking, let's say, that two-dimensional manifold, which is S1, the circle, and it's mapping it to a vector space in the category of vector spaces. That's basically what the TQFT is doing. It's taking objects and mapping it to objects. It's taking morphisms and mapping it to morphisms. So in this case, we have a disjoint union. Let's say sigma 0, disjoint union sigma 1. I'm calling sigma 0 this one, sigma 1 this one. I'm taking a disjoint union. If we map this via the TQFT, this is sending that element to, oh, actually, before I even get to that, we have in the category of cobordisms, we have this disjoint union being mapped by the cobordism to just this one n-1 dimensional manifold. If we apply a TQFT to this, it has to preserve the product So it's taking this disjoint union to a tensor product in the category of vector spaces, right? So you see in this case, another reason why I mentioned the monoidal category has to have a unit, right? So like if you tensor a unit with any other element, you get the unit back. And what I mean by this is that in the n-dimensional covariisms, in the category of covariisms, what is the unit? The unit is going to be the empty n-1 manifold. You know, the empty manifold is defined for any dimension, right? So we define it to be the empty n-1 manifold. That's going to be the unit in the category of covariisms, right? So in this case, we're taking the orientation going upside down. So up here, there's no n-1 manifold, right? So it's empty. But we're going from the empty n-1 manifold to an n-1 manifold. This is 2 dimensions, right? So it's going from empty to a S1, which is a two-dimensional. No, it's a 1-dimensional manifold. I'm sorry. It has to be codimensional 1. So basically, the unit in the category of covariisms is the empty manifold, and the unit in the category of vector space is going to be the underlying field. So that F is the underlying field. When you define a vector space, you have to define a field. You can take it as the reals, the complex, So I'm just naming it F, whatever field you choose. This is the opposite orientation, right? This is going from an n-1 dimensional manifold to the empty n-1 manifold. And so if you apply a TQFT, you're getting a map from the vector space to the field, which is a functional. So this is just the same figure that I showed you before, but here I'm giving you also a representation of what happens when you apply the TQFT to this manifold. So in this case, we had a disjoint union. When you apply a TQFT, you're getting a tensor product of these 2 vector spaces. This disjoint union of manifolds give you another linear operator here. You can call it whatever, phi or psi or whatever you fancy. So here we have a disjoint union of 3 manifolds. That takes you to a tensor product of 3 manifolds. So you get the idea. Also, for the sake of being general, these are not technically the same vector spaces. So just as the n-1 manifolds are not the same either, right? I'm just, just to keep the notation simple, I'm just giving you the same manifolds. So this is where things get interesting. We're getting to the end of this. We can use this to do something that is really special. Take any n-dimensional manifold, right? That's n-dimensional manifold that is closed. What do I mean by a closed manifold? A manifold that is has no boundary and is compact, right? So we're chopping off the boundaries in this case. So what does that mean in terms of what I told you now? We have empty manifolds on the boundaries. That means that the covariism is taking you from the empty n-1 manifold to the empty n-1 manifold, right? That's what it's doing. That M is our covariism. That's represented by the n-dimensional manifold. It's taking from the empty space to the empty space. Now we apply a TQFT to this, so we're mapping this manifold to the category of vector spaces. So what does that do? It's taking the unit. It's taking the unit in the category of covariisms to the unit in the category of vector spaces. And so this map is taking you from the field to the field itself. That's a scalar, that's a number. And what is a number? That's going to give you a topological invariant. So we have a topological invariant of that manifold by just using, mapping this to a vector space and then doing some algebra. Now, I'll give you the last example for today. In this case, we're going to look at a more general case. So we have a torus in this case. We're going to take sigma to be like something that is diffeomorphic, homeomorphic to S1, and we're going to take the cross product with S1, so we get that elongated torus, whatever, and then we're gonna cut it in half through these n-1 manifolds, so we get something like this. If we apply a TQFT to these manifolds, what are we getting? We're getting a map from the empty. In the category of covariisms, we're going, if you concentrate on this piece right here, we're going from the empty n-1 manifold to a disjoint union of n-1 manifolds. If you apply a TQFT to that, what are we getting? We're getting a map from the field to the tensor product of these 2 vector spaces, right? And then you do the same on the other half. So you're getting a map from the tensor product for these two vector spaces to the field. If you compose those two, if you take beta of gamma, what are we getting? We're getting the invariant. If you do some linear algebra, that invariant turns out to be the dimension of the vector space. Why? Because you're getting the trace of the identity map. If you take the trace of the identity map, that's just summing all the ones in the diagonal, everything else is 0. So you're getting the dimension of the vector space. And that is awesome. So here, this is our special global distance for the SAMS program. So we're here in the SAMS program, and this is our journey to our PhD. So that's a very special milestone. I want to thank everyone in this program for giving us this opportunity. It was great being here. You guys are amazing, and I'm glad to be a part of this.